Hello gamers, this is Codger speaking. With this video, I'm starting a new series about Quantum Odyssey, and we're going to start off by looking at the simple gates that are taught in the first tutorials of the game. So if you're interested in these gates and you're having a little bit of trouble with them, uh, take a look, and we think this may help you out. So let's go ahead and take a look at the Pauli-X gate. Now this is the forge. You may have seen this in another video. And this is a forge with a single qubit. The number of qubits is determined, well, first of all, it's determined over here in this circuit diagram. You can see here that there's only one qubit in it. It has two rows, which means that we are allowed to place two gates in this format. Over here, you can see that there's one qubit represented here, and one qubit can have two different states. It can have a 0 state and a 1 state. And so this line represents the 0 state. This line represents the 1 state. When the sigil, this little blue ball, is on this side of the forge, then the qubit is in the 0 state. When it's on the right side, it's in the 1 state. Pretty soon we'll look at forges that have multiple qubits in it, and we'll see how they differ from this diagram when we get there. Over here we have information about the gates and the state that the qubit is in. So let's take a look here. If you click here to give us state information, and the state information comes from a multiple of the tensor and the incoming state, or the incoming state. The output from this equation gives us the outcoming state at the next moment down in the timeline. The tensor here is a representation of what the gate does. Right now, we don't have any gates placed other than the identity state gate. And we may see an identity gate later on, but this essentially is an identity gate. An identity gate means that the outgoing state is the same as the incoming state. And so it just goes straight down. The way this works is that this is an equation, or not an equation, but a an operation of multiplication with two matrices. And the way that you multiply the matrices gives us the output for the next stage in the qubit. This is difficult. This is a difficult subject for some people. Certainly, I don't find it very easy myself. Uh, but there are places you can go and you can get some help. And one of those places is in a website that I found. Let's just go over there and look at that. And I believe that's it right there. It's called the matrix multiplication. This is a website for multiplying simple matrices. And it's at matrixmultiplication.xyz. And what you do here is you set up the size of your matrix first. So we want 2 by 2, and so we subtract one of the rows and one of the columns, and we want a 1 by 2, so we subtract one of the columns, and gives us that. Multiplication requires that the matrix that's going to, the matrix on the left, on the right, has to be equal in height to the width of the matrix on the left. And so this has to be 2 here. If it were like this instead, sorry, keep doing this wrong. If it were like this instead, and we had 2 here, you can see it's jumping around. And the reason it's jumping around is because you have to have the same height here as the width. So it's not even going to allow me to set it up so that I can demonstrate the error. Let's take a look at the tensor again, so we have that in mind. This tensor is 1, 0, 0, 1 times 1, 0. 1, 0, 0, 1, 1, 0. So let's go back to the browser page, and this is going to be a 1 and a 0. And remember, this is the tensor for the identity state. And if we multiply this, you'll see something interesting happen. So we're going to click multiply. And the first thing that happens is that the web page takes the multiplication, the right-hand multiplication, and places it on top of the left-hand multiplication to get things set up for the multiplication. We click next. The 1 and the 0 come down to this first level, and we have 1 times 1 plus 0 times 0, and the result of that is 1. Click next. We get 1 times 0 plus 1 times 0, and both of those operations produce a 0. So 0 plus 0 is equal to 0. So the outcome is 1 plus 0. And if we click next, it's going to place the right hand matrix back in, so we can see the full equation with the answer. And notice that the incoming state, 1 over 0, is equal to the outcoming state, 1 over 0. So this is the identity gate tensor. So let's reset that and go back to the forge again and place the X gate, the Pauli-X gate, at the top of the forge. And take a look at this now. And now, instead of 1, 0, 1, 1, 0, 0, 1, we've got 0, 1, 1, 0. So the zeros, the ones become zeros, zeros become 1, but the state is the same. The incoming state is 1, which represents the 0 state. And so this is in the 0 state. This says that we're in the 0 state at this moment. So let's now go back to our web page and see how this operation works. Change the the ones to zeros and the zeros to 1. And the states are the same. The incoming state is a 1 over 0, which means this 1 represents the 0 state of the qubit, and the 0 says it's not the 1 state of the qubit. Now we multiply just like we did before, and click Next. 1 times 1. 1 times 0 is 0. 1 times 0 is 0. And 0 plus 0 is equal to 0. And then we bring that down to the next row and multiply those. 1 times 1 is 1 plus 0 times 0. 1 times 1 is 1, and this is 0, so 1 plus 0 is 1. And now we'll complete the equation and compare. The incoming state now has been flipped by the X gate, which is defined by this matrix. And so the output now, instead of 1, 0, is 0, 1. Go back to the forwards, we'll see this represented by this crossover wire. So the zeros become 1s, and the 1s become 0s. Now, if we look at this state information down here, this again is another identity gate. It looks like the identity gate that we first saw, but the state now is 0 over 1 because the X gate flipped it from a 1 to a 0. I mean, from a 0 to a 1. And so that represents the 1 state. And that completes that puzzle. Let's look at the next puzzle. And now we see a similar puzzle to the last, but now the result that the forge wants us to find is to have the outcome be in the 0 state. And that's easy enough. The X gate is reversible. So 2 X gates is the same thing as 0 X gates. And so we get the 0 state to come back. Anytime you have X gates in a line like that, if they are equal, if they're even in number, the result will be the same. If they're odd in number, the result will be flipped. Now here we have a little bit more complicated situation. We've got 2 qubits, qubit 1 and qubit 2. Remember, in this representation, qubit 1 represents the most significant bit. Qubit 2, the ones on the right, represent the least significant bit. And we see that up here, that each one of these lines is defined by the values that these bits can take. This is a 2-qubit state of ket 0. This would represent ket 1. This represents ket 1, 0. And then this final one represents ket 1, 1, or 0, 1, 2, and 3, represented in binary numbers. And in this case, we want to make a change from the zero state to the one state. And the difference between a zero and a one is that the least significant bit is the least significant bit is flipped from a 0 to 1. The most significant bit is not flipped. So how do we flip the least significant bit? We do so by coming here and placing the X gate on the least significant bit. That's the bit we want to have flipped. So we place that there and notice what happens. Now, this changed from ket 0 to ket 0, 1. And that is the answer to the solution. Let's take a look at the state information for the 2-qubit situation. The tensor here changes. The state, in these simple diagrams, the state will have be a 1 where the ball or where the sigil is found in the forge. And at the beginning of this gate, at the top of the gate, the ball is in the first state, which is 0, the 0 state. This is the 1 state. That would represent the 2 state and 3 state. And so this is always going to be 1, which it's kind of confusing because this is just a different way of representing the same thing this represents, but it uses a different convention to represent it. So a 1 here means 0, a 1 here means 1, a 1 here means 2, and a 1 here means 3. In binary, it'd be 0, 0, 0, 1, 1, 0, and 1, 1. And if we look at the tensor for the identity state, it looks like this. And the identity state, you'll see this diagonal where the ones just go down. And so if this was a 1, then the tensor says that we should have an output of 1, of the 1. If this is the 2, we should have a 2's place. We should have an output of the 2's place. If this were the state, the 3 was the state, we'd have the output of the third value. And if this was the state, we'd have the output of the 4th value over here. And that's how that works. We could plug this into the browser. Let's go ahead and do that. So we can see exactly how this is working. This is going to be 4 by 4. And we want that to be 4. And we'll start off with the simple that's the simple case for the identity gate. And if you multiply this, same thing happens. It's just a few more steps. And you see that the input and the output are the same. But if you put in the X gate, the tensor is going to look a little bit different here. And let's go ahead and now look at the X gate, see what the tensor looks like. In this case, the tensor is the way that this is set up. We're only affecting the tensors in the second qubit. And so it looks, instead of just 0, 1, 1, 0, we've got 0, 1, 0, 0, 1, 0, 0, 0, 0, 0, 0, 1, and 0, 0, 1, 0. And that produces this double X here. Let's take a look at that in the browser and make this change. And that is the thing. So basically, if the 1 is here, it will be flipped. If the 1 is here, it'll be flipped from a 0 state to the 1 state. And let's watch this now. See, 0 plus 1, 1 plus 0, both of those are zeros. These are obviously 0. And so we've got an outcome of 0 for if it was in the 1 state. If this was in the 0 state, now the 1 state is zeroed out. And now 1 times 1 is 1 plus 0 plus 0 plus 0 is equal to 1. These really don't matter, but the logic is the same. And now you can see we started off in the 0 state. The 1 here at the top represents the 0 state. That represents the 1 state. And so it flipped from a 0 to a 1, just like it occurred here in Odyssey. All right, let's go on and see what else it has for us. And now we're going to make a change that will cause we want to make a change that causes the low order bit to flip, not the high order bit. The high order bit instead of the low order bit. We changed the low order bit the last time, qubit 2, but now we want to change it from 0, 0 to 1, 0, and that's the high order bit. Place an X there for the high order bit, and we get a different pattern here. And so it concludes by going to the correct location. And finally, here we have, we want to flip both bits from 0, 0 to 1, 1. In order to do that, we place an X on both bits, both qubits, and that gives us the 1, 1 result. And now we've got 3 bits, 1, 2, and 3. And we have to think about the logic to change things from a 0, 0, 0 to 0, 1, 1. And this is exactly what we did in the last one, by placing an X here and an X here. So let's pause that. Oh, let's see. I'm sorry. That's not what we did the last time. This is what we did the last time. And now it's going to go from 0, 0 to 1, 0. In the last operation, the last one that we did, if we go back and take a look at that, and that was number 5. Let's switch the puzzle back and we'll see. We wanted to go from 0, 0 to 1, 0, we had to flip qubits 1 and qubit 2 in the low orders, the low order bits of uh, of these 2 qubits, and of course that takes up all of them. Now we go here, and we're going to do the same thing. We want to put the X gate in qubits 2 and 3 because those are the bits that we want to flip. In this case, 0, 0, 0 to 0, 1, 1. And here uh, we have these X's already here, and now we want to flip. We want to change this from 0, 1, 1 to 1, 0, 0. So we want all the bits to flip, all of the bits. This is equal to that with all the bits flipped. And how do we do that? Well, in order to do that, I think I know that the easiest way is just to flip all 3 bits, either here or here, as long as we have 2 bits. We have 2 bits in each of these columns and 1 bit in this column. It should work for us. So let's try this. We'll put 1 there, 1 there, and 1 there. And that produces the outcome that we desired. And you could go like this instead. And that also produces the desired outcome, brings it to the right place. You put them down here and put them all down here if you want. And that produces the same outcome. So there's several ways that this could be done. Now we have 4 qubits in the forge, and currently the X gates flip all 4 bits from zeros to 1, and we want to change this so that only the outer 2 bits are flipped and not the inner 2 bits. And the solution to this is basically the same as the solution before. It's just place 2 X's in the columns that we want to be 0. And that is the Pauli-X gate. In the next video, we'll look at the Pauli-Z gate.